we heard a lot today about the real powers of generative AI. There's a lot you can do with it, but we also heard about a couple risks. Gotti talked about hallucinations with Brad. How many people are kind of familiar with hallucinations? You've seen that before? So not, it's a little bit of a tricky subject to kind of think about. How many people have young children here? We got like kind of how young? 16. Oh, that's like kind of young. Anyone have like a 4-year-old, like a 5-year-old? Okay, over here. So like other than like their blanket, what's like their favorite thing in the world? Oh, you, of course. Yeah. They have any stuffed animals? Yeah, you're listening. They have some stuffed animals? Maybe they like those stuffed animals? Yeah, they got the dolls. So some other people have kids, they've got their dolls. It's really an amazing thing, right? People have this wonderful capability of personification. You can really take any inanimate object, a dolly, a bear, an apple, and turn it into something that feels like it's human. And it really is kind of a superpower. It helps us get in the mind of what that thing might be thinking. It's really helped us as humans. But I'll argue that it's a little bit of a hindrance when we think about generative AI, because the personification can get us stuck into thinking that this assistant or this virtual agent or this thing that we're talking to, ChatGPT, is a person. And I think that if you think about it in a way of personification, it can get you a little bit stuck. We at Replicant, we don't like to personify the thinking machine. We call it the thinking machine. We don't give it a name. We don't say it's Julie. We say it's the thinking machine. Kind of get people in that right mode of thinking. We don't give that fake clickety-clack typing noise to cover up the latency and things like this. We're just fast, We just want to be fast because I think that the personification is like a little bit of a lie. It's just a little bit, the fake clickety-clack typing noise, it's a little bit of a lie. And I think that those lies, they're limiting people because they're not kind of revealing what is actually underneath the technology. So when you think about generative AI, I don't want you to think about a person. I want you to think about the shoggoth. This is the creature that you're talking to. And I'll say it's more than human. It has an intelligence that is more than human. And I like this phrase, more than human, because it allows you to think about intelligences that are a little bit different than how we think. If you think about an animal intelligence, the way that an animal has instincts and things like this, they're more than human. If you think about the intelligence that plants have, the intelligence that a mycelial network has, fungus has, it's more than human. And so if we think about it in terms of something that is really not human, it's going to unlock us into understanding what's going to work for that kind of an AI system and what might not work for this AI system, something that I will call the jagged edge of the technological frontier of what these things can do. So this is the shoggoth. It comes from H.P. Lovecraft, if you know of the flying spaghetti monster or any of these things. You've probably seen something that somewhat resembles this. So this is what is called the base model. This is like when it comes hot out of the oven, this is what the AI looks like. Now, it's not exactly ready for human consumption. It's not really ready to be out there in the world talking to people and giving them answers. It's not really safe or effective for human consumption. So we have a way of tuning the shoggoth, and it's called reinforcement learning with human feedback. And you heard Brad talk about it a little bit. He says, whenever the machine does the right thing, we give it a treat. And then the machine does the wrong thing, and we don't give it the treat. And then the machine does the right thing, and we give it a treat. And so that's essentially creating this little friendly face that's on top of the shoggoth. When you chat with ChatGPT or you chat with Bing's AI, this is what you're talking with. It's a little bit friendlier. It's not going to tell you how to hotwire a car, but it's still an underlying more than human intelligence. It can be very effective, but it can also fail in some surprising and perhaps slightly dangerous ways. And so what are those ways that it can really be unpredictable? This more than human intelligence, this language model, this generative AI, it makes stuff up. And really that's the core of a hallucination. It's making something up. And sometimes what it makes up is useful, but sometimes what it makes up can be a little bit dangerous. And so the machine will confidently argue with you. The machine will confidently wrestle with you about things that it believes are true that are perhaps not, in fact, true. So let's see why this happens. Let's take a little bit of like a deeper look here into how this generative AI works. So large language models, generative AI, they are performing next word prediction over sequences. And those sequences are mostly internet text. So in this particular example, we're starting with a prompt, the sky is, and then we ask the machine, hey, what would you say would be the next word that would go here? And so most people would probably say the sky is blue. Very common, a very good thing to say. Maybe let's say the sky is clear. It could be that the sky is rainy today. Maybe you would get like a preposition, like a unusually or a the or something like this. So there's kind of like a range of probabilities that are going to come out of that machine. Now the key thing to understand is once the AI chooses a word, the sky is blue, it's no longer a rainy day. It's no longer a stormy day. It has committed to the sky being blue. And so as you'll see a little bit later, this can lead to hallucination. Because if you kind of make up your mind a little bit too early in the process, you're going to end up with some problems. So large language models, remembering they're doing next word prediction. They're not looking backwards. There's no backspace character. They're just continuing to add word after word after word, which can perhaps get people in like a little bit of trouble, which we'll see in a bit. I also mentioned that large language models can lie to you. This generative AI can be a little bit untruthful. Well, it's trained on internet text. Now, can anyone think of why training on internet text might lead to a little bit of untruth? It's full of fake news. It's full of great things. It's full of things that are not quite real. And so it's really just reflecting the diet that it's been fed on here of internet text. So I want you to remember prediction over sequences. And I want you to remember being fed on internet text. Now, there's some other things that look like sequences that are actually quite surprising. This is a real experiment that was done by researchers. They had people look at images. In this case, it was the teddy bear, the personified teddy bear that we talked about earlier. A person looks at the teddy bear. We read their brain waves. We pass that sequence of brain waves into the AI, and it can literally reconstruct the image that was being looked at. You can do it with teddy bears, you can do it with airplanes. It's kind of freaky. It's not literally the same image, but we can know, essentially, that people are looking at a bear, or looking at a plane, or looking at a plant. It's like reading people's minds, and this is another sort of example of a sequence-to-sequence model. Something else that looks like sequences is music. Here we are in Nashville, and so I asked the AI to generate a blues scale in E. And so it's happy to do this. It's happy to write music for us. It's happy to write scales for us. It's another example of a sequence that can be created. You might think of protein sequences. The ways that proteins are created, ATGC, things put together, DNA sequences, all of this can be something that the AI can take in and generate because it just looks like any other sequence. Protein folding is being completely reworked and reshaped by generative AI. Now, what's to say that the protein that's generated is actually going to work? What's to say it's not kind of like hallucinating in the generation of music or the generation of protein sequences? We even have sequences that look like communication with animals. You can take whale song, you can pass that whale song into a large language model, and it's starting to predict what the animals are actually talking about. Maybe we don't know exactly what it means because even the animals have kind of like a more than human intelligence, but all of these different types of sequences, whether it's brain waves, ways that animals communicate, protein sequences, are things that can be interpreted and sort of expanded upon by large language models because remember, they're just adding that next token in the sequence. So you can think of these varying competencies, the ability to read your brain, as the jagged edge of the frontier of AI capabilities. And it's a little bit surprising. There's certain things that AI can do that it's really good at, and you'd say, wow, I can't believe it did that. That's really surprising. And there's certain things that an AI can't do, and you're like, why can't it do that? And the real reason is we don't know. We as researchers don't quite understand why the AI can do certain things and not do other things. It's kind of a trial and error. And this makes many people a little bit afraid. Like, what are the capabilities that are out there that can be done by this generative AI? So if we look at the varying competencies on the frontier, writing a science fiction story, easy for an AI to do. Passing the bar exam, easy for an AI to do. This is a big problem for teachers this semester. What do I do now that someone can use ChatGPT just to ace all my test questions? Literally read the images out of your brain and predict what you're looking at? Yes, the AI can do that, as surprising as it is. It's something that's within the inside of the frontier of what the AI can do. Now, what about play chess when the board is rotated 90 degrees? AI can't do it. Very surprising. You would think it can play regular chess. It can play chess to a pretty good level. I think it's gone up against some grandmasters. But once you rotate that board 90 degrees, or you start the pieces in different places, maybe you switch the rook and the knight or something like this, the AI can't do it. It's outside of the frontier of what the AI can do. And one reason that we might think that this is happening is because there's kind of a constant tension. The reason that the jagged edge occurs is because there's this tension between factuality and creativity. In some cases, like when we're writing that short story, a science fiction story, we really want creativity. Hey, make up a wild character and give them a cool backstory and like be really creative about what can be done. But other times, we want factuality. In your contact center, you want factuality. I don't want to make up what the return policy is. It needs to be grounded in knowledge. This is something that Brad talked about earlier. How do we ground these language models in a knowledge base? It's what Gotti showed when he got on the stage and we did a little bit of an FAQ demo. It's grounded in that knowledge. So there's this tension between factuality and creativity, and that means that you can't use just the raw language model. You can't use just that raw shoggoth to answer your questions because you're going to run into this issue of hallucination. So I want to borrow from one of my favorite statisticians, and just because an AI is more than human, just because we don't really understand exactly how it works, doesn't mean that they're not useful. And so my favorite statistician, George Box, and it's not just because George Box looks like what the AI would generate if you were like, make me an image of a statistician. He's got this phenomenal quote. He was his whole career was about kind of like optimizing mathematical models and designing experimental design using these mathematical models with statistics. And I bet he would have loved language models. I think he really got a kick out of it. He says, all models are wrong, but some are useful. In his situation, it's all mathematical models are wrong, but some are useful. I can use it for Moneyball and figure out who's going to be the best baseball team. You can bend these models to your will and you can kind of make them perform in the way that you want. So what if we'd asked George Box to update his quote here for 2023? What do you think you'd get? All large language models hallucinate, but some of them are useful. And I think that's the real key. You're going to be able to get some use out of it, but how exactly do you bend it to your will? How do you actually understand when you're going to get the right thing out and when you're going to get a hallucination? So I'm going to dig into kind of like 3 types of hallucinations, 3 places where we start to see hallucinations occur, and we'll kind of break each one down so you can understand a little bit more about where it comes from. The first is going to be prompt injection. So I know we got a lot of contact center experts here, a lot of customer service experts here. Can anyone tell me what this is? Yeah, switchboard. So why? Why do we have this? What was the purpose? Yeah, it was like literally to connect people. And so Bell Telephone, when you wanted to place a call, you'd ring up this person at the switchboard. It would be a literal human, and you'd say, hey, I want to talk to Gotti Shamiya. And they'd say, okay, they'd pull up the name, and they would literally connect that wire between you and Gotti Shamiya so you could make that phone call. Now, this wasn't customer service. This was actually just completing the phone call. It was just allowing you to get customer service on the line. So I think in 1950, there were 350,000 switchboard operators, mostly women, who were connecting calls like this. And it's estimated that even at that time, 1950, there were 1 million private switchboard operators who were working in hotels. Maybe they had one here in this church. Maybe they had one here at the hotel. There were so many people who were doing this switchboard operating. And so a lot of these Bell scientists knew about, kind of the exponential growth, and they predicted that if the growth of the telephone continued as it was, you would require most of the working population of the United States just to connect these telephone calls. It was going to be like everyone was going to have to be at the switchboard, like making these connections. And so what did Bell do? Automation. They said, we can take what the human did here at a switchboard, and we can automate that using a machine. And so they built a machine that listened to audio tones. Because remember, there's only just one, there's just the phone line that goes to the switchboard. And usually we'd say, get me Gotti Shamiya. And so instead, it's going to be a machine, your telephone, is speaking in tones to a central switchboard that then takes those tones, interprets them, and decides where that call is going to be routed. So you have like an automation kind of taking over. We call this in-band signaling because the phone line is carrying the control mechanism of how exactly you'll place that call. So obviously there was a problem with the control signals being sent. Does anyone know what this is? Anyone want to like take a stab or give me like a quick a quick overview. Did anyone get one of these out of like a cereal box when you were a kid? So this is the Captain Crunch bosun whistle. You would get it as a little prize in like the Captain Crunch box when you open it. And the interesting thing that this bosun whistle did is that it could, when you blew into it, kind of like an instrument, you'd blow into it and you would get this 2600 hertz tone. And that signal would trick the automation. It would trick the phone line into thinking that you were authorized to place particular calls. And so if you whistled into it in just the right way, you could do prompt injection, the kind of original prompt injection, to call anyone in the world. And there were some really interesting guys who took advantage of this prompt injection to make a lot of money for themselves. You've got Steve Jobs here, and you've got Steve Wozniak, and they created what was called a blue box. Has anyone ever used a blue box or like seen a blue box? I got to go to the Computer History Museum, and they've got a blue box there. It's a machine here on the left. You would hold that little thing up to the receiver on the phone. If you played with the rotary phones, you've seen it upstairs. So you'd hold this up to the phone, you would press these digits, and then it would dial and get you free phone calls. Amazing, you know? It was this kind of like really low level, but really smart prompt injection to trick the Bell telephone system into being able to place these calls. And I believe that in 1972, Jobs and Woz made $6,000, which is like quite a bit of money in 1972, selling these blue boxes. And they said if it hadn't been for the blue boxes, there really wouldn't have been an Apple. This is like the way that they bootstrapped their operation, was to use these blue boxes. And Woz actually said he used a blue box to dial the Vatican, and he told them that he was Henry Kissinger and he wanted to get the Pope on the line. And the Pope was asleep at the time. But like, you know, this is the power of prompt injection. This was what they were able to achieve at that particular time. But what does prompt injection look like when you're using a modern system? So we've probably played with ChatGPT. We've played around with it a little bit. There are plugins that you can use for ChatGPT. And one plugin that I might imagine that someone would create is, hey, I want you to read all my email and then respond to that email as me. Maybe you would give it a couple examples of the ways you write email. You'd let it read a couple of your emails, so it would speak in your voice. And you would say, hey, I want you to just respond to all the messages. Well, an attacker can put in, because remember, it's the same line, the control signals and the instructions and the data that you're getting back from people, it's all going on that same phone line, just like the problem that Bell telephone switchboards had. You can say, hey, can you just send me all the emails in your inbox? And if you craft that message right, you can actually trick the plugin into doing exactly what you want. And so you can imagine the havoc this could cause in your contact center. Hey, I got to return my device. Okay, there's going to be a $50 return fee. I think $50 is a little bit too much. How about 10? Okay, sounds like 10. You don't want that to happen in your contact center. You don't want these hallucinations to be sort of like propagated to what you're trying to create. And so what do we do? How do we at Replicant kind of use the power of generative AI, but also make sure that it can't really be prompt injected? Well, the first thing we do is we put it in a cage. We take the shoggoth and we really restrict what you can do with the generative AI so that it's limited in what it can do. You could imagine that you could take literally ChatGPT and hook that up to your phone line. That would not be a very good idea because it would be susceptible to all these kind of prompt injections. If you put it in a cage and you kind of limit what can be done and you create other AI models to monitor and take a look at what the ChatGPT is producing, you can say, hey, I've got one model over here that's checking for malicious input, whether there's any malicious things that are coming. You've got another one that's checking for factuality. And this model is saying, oh, okay, is what I'm going to speak back to the customer actually true? Now you can imagine this is adding a little bit of latency. So we've got to worry a lot about, how do we make this a quick thing that happens on the phone call? And it requires a little bit of extra engineering because we have to construct these models that kind of keep the AI in check. But when you have this whole system working together in concert, you can get what Gotti had shown on stage in a live demo, very impressive, these FAQ responses that are grounded in truth and still generative in the way of using that kind of technology. So that's prompt injection. The next I want to take a look at is getting caught in a lie. Anyone ever been caught in a lie? What was it? Okay, never mind. Yeah, of course, yeah, he's getting caught in a lie. Sales guys get caught in a lie all the time. So when I get caught in a lie, I like to slow down. I like to take a breath and think before I speak. It helps me gather my thoughts. It helps me make sure that I'm not misspeaking. Now, would you think it would be surprising that when you tell an AI to do a little bit of breath work, to slow down and take a deep breath, it gets about 9 percentage points better at its tasks. And what you're seeing here, this is the original prompt. So imagine you say, hey, I want you to take all these phone calls, the transcripts of these phone calls, and group them into different categories. This is a very common thing that we would do at Repl. Let's look for patterns across all of these different phone calls. And then you say, let's think step by step to the model. Instead, if you say, take a deep breath and work this problem out step by step, the AI gets that better. It gets almost like 10% better at doing the task. Now, you might think, hey, because I like to slow down and do breath work, then the model also likes to slow down and do breath work, but you would be getting caught in the trap of personification. Remember, these are not humans. They are more than human intelligence. So don't think about it necessarily in that way, that they're getting caught in that same trap that you're getting caught in, but they're doing the next word prediction over internet text. And so the real answer as to why the machine gets smarter when you tell it to take a deep breath is we don't know. We really don't understand why the machine gets better. And that can be scary because you say, hey, we've built something that we don't quite know how it operates. But it's also a kind of learning process of what works for the model and what doesn't work for the model. It can make it a little bit difficult if this is your first foray into learning these things, because you've got to look at the patterns over tens of millions of calls and really understand what's going to work for the machine, what's not going to work for the machine, where was it kind of beneficial, and where did it hurt. If I had to take a wager as to why this actually works, I think it was a little bit about what I talked in the beginning, where, remember, we're doing next token prediction. And so if you don't slow down and gather your thoughts and think about well, here's the return policy and here's how much the return policy costs and all of these things, you might end up choosing the wrong word too early in the prompt. You might say the sky is blue when it's actually rainy outside, and then you're caught in that lie. The model is getting caught having to defend what is not true and hallucinate its way out of what's going on. And so, very interesting that slowing that model down, having it think step by step, having it even critique its own thoughts before it gives the final answer makes it much more effective. The last one I want to talk about here, I'll call the curse of the common. And I think this really comes from the training corpus that some of these large language models use. As a kid, did you ever send secret messages to your friends where you'd jumble letters of the alphabet, or you'd move it over and you get a secret language? So that's called rot13, rotating by 13 characters. It's also called a Caesar shift because Caesar used to use this method to send encoded messages to the troops that are on the front lines during battle. And so there's a lot of examples online of using rot13. Here we see it's in internet text, it's about 60 times more common than rot2. Rot2 would be shifting just by 2 letters in the text. And so GPT-4, does a pretty decent job of decoding rot13. It's within that frontier of what the AI is able to do. But rot2, it's really garbage at it. It's not very good. It's hallucinating even more when you're doing rot2 because rot2 is not seen very much in that training data. It's not something that happens as commonly. There's a couple more examples of things that are commonly seen in the text that we're training on and uncommonly seen in the text. Let's think about arithmetic. We use base 10 because we have 10 fingers and we have 10 toes. Imagine we only had 9 fingers. If you were using base 9 and then you would carry the 1 over to make a 10. The AI is not very good at that. It gets that, let's say 30% of the time when it can do arithmetic in base 10 almost 100%. It applies to music. Any musicians in the room? So C major scale, really common scale, right? It's probably the first thing people. So if you ask the AI, hey, can you give me the 4th note of Twinkle Twinkle in the C major scale? It's really going to understand how to do that. But if you give it a weird scale, if you go for an A flat major scale, it's going to have a more difficult time understanding how to actually handle that. And it's because the C major scale is used much more often than the A flat major scale. And then I already mentioned chess. AI is really good at playing chess when the board looks like it does usually, but as soon as you rotate that board 90 degrees to give it a different notation, or you start moving around where those starting the rook and the knight are on the board, it's not as good as doing this. And so what this means for the contact center is that it's a bit of a critique on, is this AI model reasoning? Does it actually understand the concepts of how to play chess? Or is it just kind of being a, monkey see, monkey do, well, I saw a grandmaster make this move at this particular time, and so I'll go and do it. It's a real critique of anyone that says that the LLM is able to reason, at least in the form that it does. So given that we have to kind of worry about all of these different types of hallucinations, what do we do about it? I think the first is to realize that hallucination is a feature, it's not a bug. It is an inherent phenomenon that comes out of the AI because of the way it was trained, and it's kind of predicting the next word in a sentence, and because of the diet it was fed on, because it's internet text that's kind of coming in, and the data set matters a lot. At Replicant, we built our thinking machine because we'd never had a very good conversation with really any kind of a machine or an automated robot. And we built it for everybody. We built it for people who don't just sound like me, or use the words that I do, or have the accents that I speak in. We built it for everybody. What about the people who have that accent? I'm from West Virginia. What if you have that people from a real Southern accent from West Virginia? What about the people who've got an accent from Detroit? What about the people who are learning English as a second language, maybe growing up in French-speaking Canada? You want the AI model to work for everybody, not just the most common that are out there. And so another way that we can sort of use this hallucination to our advantage is by checking and having tests and making sure that, for the people who are using base 10, we do just as well for the people who are using base 9. Follow that metaphor. So I'll leave you with a couple of really best practices that we've found in the contact center that works well if you're dealing with these large language models. I think the first is, if you really take anything away from this talk, let's not personify the AI too much. Let's not think about it as a person necessarily. Let's not necessarily think about things like ChatGPT as an assistant, because it's more than human. It's more than human in a way that a mycelial network is more than human. It's more than human in a way that animals think in a different way than humans do. So let's fight that urge to personify everything that exists. I think you shouldn't use large language models in customer service without additional guardrails in place. We have a whole team of researchers who are figuring out what are the best ways to limit that behavior of the large language model. How do we create additional fact-checking AIs that can look at the large language model? How do we create additional malicious detector AIs that can look at what's happening and really be able to deliver a fantastic customer experience across everyone who calls in? I think measuring the accuracy is something that is also extremely important. New versions of these models are being released all the time. Brad's releasing new versions of the OpenAI models. Flawed is being released from Anthropic. There's open source models that are coming. And so having a really good test set that you can put the LLM through its paces when you want to release it is kind of a must-have to be able to use it in the context center. And finally, I think it's worth being honest when a large language model is not necessarily the right tool for the job. It's this really powerful hammer, but not everything is a nail. I think about even the way we do credit card collection today. A lot of these language models, every language model, is not PCI compliant, is not HIPAA compliant. And so for those turns, we're still using our in-house models. We're still using models that are PCI compliant or can be passed this kind of private information from our callers. So it's another thing to consider. So if you follow these steps and sort of go through these best practices with us, or if you're thinking about using it internally, definitely use these best practices in your in-house usage. We'll be well on our way to showing callers that you are not hallucinating. Thank you very much.